Hello. Yesterday I showed you a video, or sometime you saw a video about U substitution and just talking about the algorithm. I would like to demonstrate the algorithm a few more times for this video, but I would also like to talk about the understanding, particularly the notion that we have an integral with respect to x and we use the dx. Recall that the dx represents the infinitesimally small change in x for every one of the little rectangle slits that we make under the curve. But in order to do u substitution, we have to change the variable of integration from x into u, or whatever it is we're substituting by, so that we have du instead of dx. What I'm trying to do with this illustration is to show you how change in x on one function, when we make a u substitution, that same change in x, here I showed it from 1 to 2. If we show a change in x from 1 to 2, allow x here to change from 1 to 2, it means that the u's go from 3 to 6. So a change of 1 in x corresponds to a change of 6 in u. That's just for the interval that I showed. But the point is, there is a direct connection or correlation between change in u and change in x. So here's how we find it. Again, with the u substitution algorithm, we have u is equal to some function of x, and then all we have to do is take the derivative with respect to x. We get 2x dx is equal to du. So what that does is it basically says this is the connection that says how to transform your delta x into a delta u that then becomes a du. So what I'm trying to do with the calculator images here is to show you that I can integrate the given curve from any boundaries I want, and in this case I went from 1 to 2, and it gives you a specific area. If I take the u modified curve, this time I don't go from 1 to 2, I go from 3 to 6. But if I find the area of the u curve from 3 to 6, it gives me the exact same area as the x curve, the y curve, between 1 and 2. So this little shaded area here is the same as that little shaded area there. The whole purpose of this is to show you that when you change the variable of integration from x to u, you're also changing the boundaries, because you're going from change in x to change in a different function of x. So that's something that we'll observe as we move on. But hopefully that's a helpful illustration. If not, we'll just study the algorithms and memorize the crap out of them. As per usual, we have to be careful of this one. It's actually the cube root. It's not x cubed. I had to think about that one for a second. But we always look at the inside of the most complicated function and take its derivative. So the derivative of x squared is 2x, and I see here is a 6x, which basically means this is going to be part of my substitution, and this is going to be my u inside the radical. Let u equal x squared plus 4. That means du is equal to 2x dx. So I'm going to take, oops, that went a little fast. I'm going to take, as you can see here, I have 6x dx. I took 3 of that and took them outside. That left me with a 2x dx. Here I took the 2x dx, and I can replace it with du. Oops, there we go again. Got a cast on my right hand, so I keep mashing the buttons. So here, the 2x dx becomes du by my substitution relationship over here. And then instead of the cube root of x squared plus 4, I write the cube root of u, which is written as a 1/3 power. Put it in a power form. Then we take the antiderivative, and then we put u back where we found it. And so just to verify, once again, just a reminder, if you put in your integral in Desmos, and then you put in the given equation as it was written for you, and then you take the derivative of your answer and the given function, the derivative of your answer plus the given function should be the exact same graph. Here, as you can see, there's green, and the red doesn't exist because it's underneath the green. They're the same. So that's how you check. So for here, we're going to let u equal x plus cosine of x, just because that's the inside function. And then when I take the derivative, I get 1 minus the sine of x dx. So that means we could take our integral and separate into the stuff that will turn into du and the stuff that will turn into u's and other things. I take my cube root and make it a 1/3 power. That way I can clean all this up to that integral. This is so much nicer than having to integrate that beast up in there. So you can start to see the benefit of u substitution, especially for these, corny prefabricated problems. Nonetheless, I put my x cosine of x back into where I found it, and re-express the interval or the integral in radical terms. So we have the cube root of x plus cosine of x quantity squared times 1.5 plus whatever our constant is going to be. Of course, I will check that with technology, but this is about the algorithm. So once again, inner function, take the derivative of both sides, and as you can see, this starts to become really, really commonplace. What makes this one a little bit different is that I have 4 over x squared dx that I need to change into u. And when I did my du here, I got -1 over x squared. So I wanted this to be a positive 4 over x squared, so I had to multiply both sides by -4, so that I get 4 over x squared dx is now going to be substituted with -4 du. And that's done. Let's bring out the -4, easy integral, put our u back where we found it, and check our answers, and we're good to go. Here again, I actually am just going to fly through this one. If you want to see how this work is done, you'll see it's the same thing. You know, again, the only twist here is when I take the derivative of my u value, I'm off by a little bit. I want 2 over x squared, and I have -1 over x squared. So I multiply by -2, just like in the last exercise. But then we get to this one, and the reason I wanted to bring up this one is it says the a value is unknown. That's the coefficient on x. When we integrate with respect to x, that a should be treated like a 4 or a 2 or a 7 or any other nice number. Treat the a like a number, a constant. So what that does then is it tells me when I take the derivative of my u, which is the inner function, I get -a times e to the -ax because of the chain rule. And then if I was to solve that for e to the -ax dx, I get my du transformation. So all of this stuff here becomes u to the 1/2, and all of this stuff here becomes du over -a. Take the -1 over -a out, because it's constant, and then I'm left with just u to the 1/2 du, easy integral. Put the u back where you found it, and check with the technology in case you're not sure. I was a little bit reticent because this is a pretty funky looking result, but the nice thing is you can even put a and then put in a slider and make a anything you want, and you should still have the green graph overlap the red graph exactly, and that's what I have here no matter what value I choose for a. So that feels good. You can even check your answers with Desmos even if you don't know some specific constants or coefficients. And last but not least, I saved this one because it sure requires a little bit of foresight, and it's also an example of double U substitution. Not double U substitution, but U substitution twice. I'll show you how it works. We start with what I think would be the obvious, which is take that inner function, or maybe this is the inner function, but it's the same, 1 plus e to the 2x. And I'm going to let u be that, therefore du is equal to 2 e to the 2x, or half of du is equal to e to the 2x dx. Let's see if that dx comes back. It never came back. All right, let's get back here. A little typo for me. Oh, come on, go ahead. Sorry, you guys got nowhere to go, I hope. Just hanging out watching somebody do math. 2x dx. Oops. So, moving on. Then when we make our substitution, we're actually going to get 1 over u times the natural log of u times the du times the -1/2. So once again here, I'm going to take out the -1/2 because it's constant, or the +1/2, whatever. And now I see what I'm left to integrate is 1 over u times the natural log of u. And I see that that's a product, but more importantly, I know that the derivative of natural log is 1 over u in this case. And so I'm going to do another substitution. This time I'm going to choose the letter v. V is equal to the natural log of u. Then dv is equal to 1 over u, du. Which enables me to take down the 1/2. We got that. Then the natural log of u becomes v, and the du over u becomes dv. Simplest integral ever. Well, maybe not, but pretty close. We're going to get a half of v squared times the other 1/2, and we put our u back where we found it, and then we put our v back where we found it, so that we eventually get 1/4 natural log of 1 plus e to the 2x. The natural log is squared as well, plus c, and I was really nervous about that one, so I definitely did a little technology check there, make sure everything's copacetic, and in fact it is, so points for me. So I hope you find that helpful. Again, this is rudimentary and it's a long video, but for those of you that are struggling, what this is for is to give you extra exposure to u sub. Thanks for watching.